This is the second part of our lesson on acid-base properties of salts. Please make sure you have viewed the Khan Academy video before viewing this video. Let's do a quick review of what you learned with the Khan Academy video. You should have set up a table in your note worksheet, and that is similar to what I have listed on this slide. When we're looking at a reaction between a strong acid and a strong base, our salt solution should be neutral. When we look at a reaction between a strong acid and a weak base, we will have a salt solution that is acidic. And the last scenario is looking at a weak acid and a strong base, and in this case our salt solution will be basic. The only combination that we haven't looked at yet was a weak acid and a weak base. So this video will look at that scenario. With these types of reactions, we will compare the values of Ka, the acid dissociation constant, and Kb, the base dissociation constant. Just as a reminder, the Ka values can be found in your text on page 628, and the Kb values can be found in your text on page 647. By comparing the Ka and Kb values, we can determine if a salt solution is acidic, basic, or neutral. And I've given you here on this slide a little summary that you can refer back to as you're working through problems in your textbook. If the Ka is greater than the Kb, then the salt solution will be acidic. If the Ka is less than the Kb, then the salt solution will be basic. And if Ka is equal to Kb, then the salt solution will be neutral. To solve these types of problems, you will need a calculator and you will have to use some basic math. The equation that we're going to be working with is Ka times Kb equals Kw. And if you remember from past lessons, Kw is H plus times OH minus, or hydrogen ion concentration times hydroxide ion concentration. And we talked about that earlier in this unit. I'm going to quickly show you how we derive the Ka times Kb equals Kw, and we're going to use the acetate ion as our example. When we look at the acetate ion and we think of it as an acid-acetic acid, as we can show here in this first example that I've starred, you can see that the hydrogen ion dissociates to form the acetate ion, and then you can also see the acetate ion acting as a base in the reverse reaction, where it's going to actually take a hydrogen from the water and reform the acetic acid. And you can see that then, with that hydrolysis of water, we are left with OH ions in solution. And that's shown by this second reaction that I've just starred. So now what I want to do is I want to set up the Ka expression and also the Kb expression for both of these reactions. So I'm going to move on to the next slide to show you how we've derived Ka times Kb equals Kw. So I've written both the Ka expression from the reactions on the previous slide, and you'll see that I have in the Ka expression, in the numerator, I've taken the products of that particular reaction, which was the hydrogen ion, and multiplied it with the acetate ion. And then in the denominator I have the reactant, which is acetic acid. And then you can see I did the same thing for the reaction where we have the acetate acting as a base. And in the numerator I have the hydroxide ions multiplied by the acetic acid, and those are our products, and then I have that divided by the acetate ion, which was a reactant in this case. Now, if I multiply these two expressions together, Ka times Kb, I'm going to have something that looks like this. And just give me a second to rewrite this Kb expression so we can multiply them together and see what cancels. Now you can see here when I multiply these expressions together, I have the acetate ion in the numerator there and denominator here, so that cancels. And I have acetic acid in the denominator on this side and in the numerator on this side, so that cancels. And what I'm essentially left with in this reaction is the concentration of H plus, whoops, times the concentration of OH minus. And so that is why we can say Ka times Kb equals Kw, because in essence we're saying the hydrogen ion concentration times the hydroxide ion concentration equals Kw as well. You also need to remember that Kw equals 1.0 times 10 to the negative 14th. Whoops. There we go. Add that one in there. So let's take a look at an example. If the product of a reaction is the salt ammonium cyanide, we need to figure out what these ions are doing in solution. Just as a reminder, I would like you to notice that I put the reference pages for Ka and Kb values at the top of this slide. Let's first look at what's happening with ammonia in solution. I apologize, ammonium ion in solution. It's actually going to act as an acid, and it's going to dissociate into ammonia and hydrogen ions. Because it's acting as an acid, we need a Ka value. But in our textbook, we're not given a Ka value, we're actually given a Kb value for ammonia. So we can actually solve for Ka by using the Kw and dividing by Kb to solve for the Ka. So in your textbook, you're going to notice that the Kb value is 1.8 times 10 to the negative fifth. So what I've done is I've set up the equation to take the Kw, which we know is 1 times 10 to the negative 14th, and I'm going to divide it by 1.8 times 10 to the negative fifth, which is the Kb, and the result that I get is 5.6 times 10 to the negative 10, and that is going to be our Ka for ammonia. And the reason I did that, again, is because ammonia is acting as an acid in solution and donating a hydrogen ion to this solution. So that's why we solved for Ka. Now we'll take a look at the cyanide ion. Cyanide in solution is going to actually act as a base because it's going to accept a hydrogen ion from water, and it's going to leave hydroxide ions in solution and form hydrocyanic acid. So we actually need the we need to solve for the Kb because it's acting as a base. We know the Ka, we can get that from our textbook, and the Ka value given in our textbook is 6.2 times 10 to the negative 10th. I'm going to take that number and divide it with the 1 times 10 to the negative 14th to solve for the Kb, and that gives me a value of 1.6 times 10 to the negative fifth. This is my Kb value for this particular reaction, and now all I need to do is compare the Ka value with the Kb value, and you can notice here that Kb is larger than Ka. We have 1.6 times 10 to the negative fifth for our Kb and 5.6 times 10 to the negative 10th for our Ka. So because Kb is greater than Ka, this solution is basic. You will not always need to calculate or convert Ka and Kb values like we did in this example. It just all depends on what ions are in solution and how those ions are behaving in solution. In this case, we had ions that were behaving, in the case of ammonium, was behaving as an acid, but we only knew a Kb value, so we had to do a conversion. That won't always happen in problems, as you will see when you work through some of your homework problems. We do have one last type of problem, and it's the highly charged metal ion type of problem. These are looking at metals like iron and aluminum, and these solutions are always acidic because the metal ion will hydrolyze the water or break apart the water, and that will form hydrogen ions in solution, and then it will form a metal hydroxide. And because it hydrolyzes the water and forms this hydrogen ion in solution, as you can see here in the reaction that I'm showing in this example with aluminum sulfate, anytime water is split and that H plus is formed, it causes solutions to be acidic. So anytime you're working with highly charged metal ions like iron or aluminum, you're going to have salt solutions that are acidic. Now let's talk about the assignment that will be due with this particular lesson. I would like you to add to the table that you started in your note worksheet to include the information we discussed about weak acid, weak base, and that's where you're comparing the Ka and Kb values. I also want you to include the highly charged metal ion situation in that table as well. And you should do this on your note worksheet. You should also complete problem number 111, which is found on page 676 of your textbook. You should also include this in your note worksheet after the summary table. You should submit this to the designated Dropbox. If you have any questions, please email me or use the discussion board. The discussion board will allow other classmates to see answers to questions that you might have, that they might have the same question. But if you prefer to email me questions, you may do that as well. Please make sure that your note worksheet is handwritten, and I will not be accepting photos of your note worksheet, so please make sure you're saving them as PDFs and submitting them in the appropriate Dropbox.